Managing devices at the edge is challenging. They're distributed, hard to access physically, and often mission critical. Flight control makes this manageable with centralized control, GitOps automation, and full visibility. In this demo, we'll focus on kiosks, onboarding devices, organizing them into fleets, and watching them adapt content automatically. It starts with generating a config file via the CLI. A flight control agent runs on each device, and this file contains everything needed to connect to the flight control service. After booting a device whose image includes the agent and config file, we can move to the UI and see the device pending approval. The agent provides the service with identifying information. If we recognize the device, we can approve it. At this point, we can assign an alias and labels. Labels have several uses: querying by groups and assigning devices to fleets. Since we haven't defined fleets yet, the UI informs us this device won't be part of one. After approval, we see the device is healthy, running a basic CentOS bootc image. We can modify the individual device directly through the UI or API, useful if you're not ready for fleets or GitOps. We'll leave the alias, labels, and system image unchanged and add a configuration file inline in the UI. We can also specify external sources for config files, like Git or HTTP. More on that later. We'll add a simple message of the day using default permissions and update policies. Now, if I click Terminal, the system establishes a gRPC-based connection to the device. There, I can view the contents of the updated file. This connection is initiated by the agent, so it works behind NAT. No need to open ports on the device. Now let's create our first fleet. We could do this via the UI, but instead we'll use a GitOps flow. First, we define the Git repository that hosts our kiosk content. We provide the GitHub URL. Since it's public, no authentication is needed. We'll use this repository later. Next, we create another repository for our fleet definition. We provide its GitHub URL as well, but this time we also create a resource sync. This tells flight control to sync the fleet resource from a specific path in the Git repository into the system. After a short time, we can see flight control has observed a git commit hash. A fleet resource was created. Let's look at its definition. It has a name and a label selector. Any device with the label type equals kiosk will join. The UI shows no devices currently match. The template defines a new bootc system image and tells flight control to pull kiosk content from the v1 tag in Git, placing it in the var kiosk catalog directory on each device. Notice the path property includes a parameter. Flight control uses a different path in the Git repository depending on the device's region label. If we check the Git repository, we see a Content US East directory with 3 products and a Content US West directory with 3 different products. Back in the UI, we define a simple Podman Compose application that runs a Python HTTP server to serve the content flight control pulls from Git. Advanced options like rollout policies, disruption budgets, and update policies are available, but we'll skip those. And since this fleet is synced from Git, we won't save manual changes in the UI. Now let's have our Boston kiosk join the fleet. All we need is to set the region label to define its content and set the type label to kiosk. The device immediately joins the kiosk's fleet. The UI shows it's running the wrong system image, so flight control updates it to match. Once it reboots, we can see our kiosk app in action. Let's add a second device. Imagine an operator approving the enrollment request. They identify the device, set an alias and a couple of labels, and the device is onboarded with the correct content. This kiosk is in the US West region, and after flight control syncs the content and reboots, we see it runs with different content than the US East kiosk. For the final step, let's update the fleet definition in Git. We'll change the content to use the v2 tag, which makes the logo in the background spin. After committing the change, flight control picks up the new commit. The fleet is now configured for the v2 content, and flight control is already updating devices. Once they reboot, we see the spinning logos in the background. Flight control brings secure onboarding, fleet management, and GitOps-driven updates to edge devices, delivering consistency and automation everywhere, from kiosks to factories, retail, transport, energy, and healthcare. It scales across industries, centralized, visible, and reliable, wherever your edge may be.